as I say, there is the agenda quickly. Just what a PLC is, how the PLC program scan works, the organizational blocks, the additional programming blocks, and then I would just go through quickly the memory areas and explain how the bits and bytes and words work, and then I will just actually show you some projects where we've configured the PLC with step 7 and TIA. Like I said, this is going to be primarily based on Siemens. So step 7 is still, in my opinion, better than TIA, but they're pushing us to TIA. Then there's the clock byte, which I want to just describe to you because it's a really nice feature to have, but it does take up a marker or byte. And then we'll go through some extra stuff at the end. Okay. So there's a PLCs. That's my official understanding what a programmable logic controller is, PLC. A PAC, like I said, is a programmable automation controller. And I know of more, and there's one or two other ones that call them PACs, but they really aren't so clever. This one at the top is a Siemens S7400. This one in the middle is the S7300. And this one on the left is a Mitsubishi. That is a Modicon. The one on the left is a Modicon. That's an M580. That's a nice beast of a PLC. There's your Allen Bradley. That's the old one, PLC 5. This is PLC Direct. Not much to write home about. And this is a new one, Arduino PLC. But both of these suffer from not really having a very good programming space, and they use Codesys, or in fact, they might even use Node-RED on Arduino, which is not a pro PLC. Anyway, so I think I've explained this to you guys a couple of times, but just remember the PLC program scan is, it's very important that it always does this loop, but just before the PLC starts, when you power on the PLC, it actually, in some PLCs, checks the PLC program that it's not corrupt. It obviously has some memory checks on it. Then we'll restore any stored values in the data blocks or the memory variables that are set on restore. And then depending on how you start it, they talk about in Siemens, a cold, a hot, and a warm restart. Cold restart is one where it's been switched off, and then it is switched on again from 0. A warm restart is when you actually tell the PLC to stop from the programmer, and then you start it again. And the hot one is when you use the switch on the front of the PLC, and you stop it and you start it. Now, I may well have the hot and warm back to front, but it's something like that. So once it's gone through those things, and the cold, hot, and warm restart have got special organizational blocks that it will call to do anything specific you want it to do. Then it will go into the main program scan. Now in Siemens, that's called OB1, whereas in some of the other PLCs it's called main. And then you can have different programs configured. They call them program units or something, but it's the same as our Siemens modules. So once OB1 is running, it always reads all the states of the input cards, then stores them in the input area, the input memory area, then executes the PLC program from start to finish. In that execution, the inputs are never read again. They don't change at all until at the end of the program, it writes the outputs that your program has now put on, and then it goes back and it reads the inputs again. So that scan time in a S7300 could be of the order of 10 to 50 to 100 milliseconds, depending on the PLC type and the model. Whereas if we go to the new S7 1500s, they're running at 1 millisecond. So they really are flying. So that is just, so the OB1 is where the action is. From OB1, you can literally write everything in OB1, but that is just poor structure. But from there, you will then jump out and call a function block or call a function FC, they call it, and etc. So you will structure your plant in different blocks being called out of OB1. But let's just go quickly to to the organizational blocks. Siemens has got quite an impressive feature. And I know, in fact, in the older PLCs that I worked on, they also had a similar mechanism where two things. Siemens has got these things called OB30 to 38, and literally you can have this program interrupt the PLC every 5 seconds or 2 seconds or 1 second to do something specific you want to do at a set interval. Now that typically is where you're going to do PID loops. With PIDs, you want to typically run them at a continuous, the same scan time all the time. But you might have some special controls that you might want to do in these shorter ones. But remember, I'll explain on the next slide why you must be careful. Then the Siemens also has a way that you can hardwire into an input byte. I chose input byte 0, and if one of those inputs come on, it will then jump to OB40 or 41 or 42, depending on which input comes on, and it will interrupt OB1's scan. So you can have something specific that happens when that input comes on, and it can do that in the scan while the scan is running. Okay, right. So here's typically how the PLC works. OB1. Okay, I'm going to talk a lot on the S7300s because they run a little bit slower, and I want to. And in fact, in older PLCs, you could set the scan time to say 50 milliseconds. So if the program took 5 milliseconds to run, it would run and it would wait for the next 50 millisecond and run, and so on and so on. Then you can see what I did to try and explain these OB40. Basically what happens, if this OB1 is running the program and it gets input 0.0, it will interrupt OB1, it will go to OB40, do the logic there, and then come back. So what will happen is it will extend the scan time while it goes and processes OB40. Now, this is typically how it works. You must, if you get more than one input 0.0 during the scan, you could actually make that scan time get longer and longer and longer. And eventually the PLC's got a timeout that the scan time is overrun, and then it will trip. So one must be very careful how you manage what you do in OB40, say. It mustn't be a massive program. It must be very quick in and out, and so that you don't cause scan time errors and you don't cause other inputs and outputs to lose control. Everybody understand so far?
Yes, Mr. Tim.
Okay.
Yeah.
All right. Okay. So
Yes.
Cool. All right. So what you're going to do in your OB1, I'll just flip to the PLC quickly. OB1, here is a plant which we did at Food Corp. It's FML. Can you see that, or must I make it bigger? I can't zoom. Can I zoom? I can't really zoom. Okay. So if I go into OB1 in this plant, I'll actually zoom here if you want. Although the font gets a bit messed up. But so what this program does, you see, it's actually got networks, and it's calling different program blocks. Or in this case, these are FCs. If I just move my mouse there, it'll show you. It's FC700, etc. So this program is the controller of the whole software. So we will then call blocks to do certain things. And you can see, even though the PLC has read the inputs, we actually map the inputs into a DB. We then also call the Profibus in this project to our network comms, etc. Then we call all the function blocks for all the controllers. We do some safe starts, I'll explain that later, call the sequences, and then we write the outputs back to the outputs, and we end the program, and then the PLC will continuously loop through this program. So if I just go, let's say I go to DI, if I open this block, you'll see it's actually got the input blocks there. This one is direct, this one hasn't got many, so it's all in one block. There's another function block call, but notice that is the same function block as that one. So it's calling that same function block repeatedly with different inputs. And that is a structure that we use. So let me flip back to this. All right, so that's OB1 in principle. OB1 does that. In this plant, we don't do any OB40s or OB30s because that's quite a simple plant. So we have, in the program, we would have typically function blocks. Now, function blocks are typically the built-in function blocks. So if I go back to my program, sorry, I'm going to go here, and I just call up the program menu here as such. All of these function blocks here, like, let me go to the libraries. All of these function blocks are inbuilt. Let me go to built-in. You see now they've got a special name there, SFB and SFC. Those are special. They are inbuilt in the PLC and they have all different functions and you can call them. But typically in the older PLCs, I'm just going to go, see here they call them FCs. Where is my FB? See there I've made an FB14. That is actually an inbuilt function block. If I just go to help, it will actually tell me what that function block does. And I can literally go and, the help is very good in Siemens. You can go and see a lot of stuff, but I'm digressing. Okay, function blocks, typically inbuilt function blocks. We don't use those anymore in S7 because they are standardized for inbuilt blocks. And I see at the bottom I put SFBs. In the older S5 PLCs, they used to have what they call program blocks, and those are programs that call function blocks. So it's the same as the new FCs, and you see the little star here. We use FCs now. So we have FCs for everything, and that calls maybe inbuilt function blocks, or it calls other FCs, and that is typically what we use. So we don't want to stray away by using function blocks, because if we ever want to use an inbuilt function block, it's going to cause a problem. It's got the same function block number, and we cause lots of issues. So stay away from them, use FCs. Okay, so the next thing is memory areas. I just want to show you here, as the PLCs have got bigger, but in the good old days, in the S5 PLCs, they used to have digital inputs and outputs, and they were called I 0.0 to I 0.7, so 0, 1, 2, 3, and they're all individual bits. Then it goes I 1.0 to 1.7, and it goes all the way up to 255. That was the maximum size you could have in the older PLCs, 256 bytes of I inputs, which is 1024 digital inputs. And the same for the digital outputs. The Q is the output, and it works the same. They're individual bits. Those are digital inputs. then you have for the analog inputs and outputs, they are called peripheral input words and peripheral output words. P, Q, W, and P, I, W. And in the olden days, they were always at 256. So you see the digitals were 0 to 255. And the analog started at 256. As the newer PLCs have got bigger and bigger, we can actually allocate them anywhere we want. But it's still advisable to keep a separation between digitals and analog. So you'll see in all the programs we use, we still stick at 256. It's just a norm. We don't want to make it difficult to know where everything is. All right. Now, this is very important for you to understand how the bits work. In the digital inputs, they are all I 0.0, 0.1. They are all separate bits. It is stored in the PLC as bits. But then what happens is you can group the first byte. See, that's 8 bits. That is called a byte. So input byte 0 is actually all of those bits in a binary number. So So 2 to the 8 is 255. So it will go 0 to 255. You see how it's still 255. So input bit byte 1 is those 8 bits. Input byte 2, 3, etc. Oh, I made a mistake there. It should be a 3. Anyway, now if you wanted to use, say, the whole word, 16 bits of the word, you could actually address it as input word 0, but it's still technically input byte 0 and input byte 1 as one long 16-bit word. But it's still got I input I 0.0, 0.1 to 0.7, and I 1.0 to 1.7. That gives you 16 bits, and that's 0 to 32,768. But it's actually 0 to 32,767, and negative number. Oops, I don't know why what's happened to my thing here? And negative 32,768. Anyway, it's a positive and negative number. The final bit 1.7 would be the sign, whether it's positive or negative. Then you have double words. You can have double words. So if you reference input double 0, it's actually input byte 0 and 1 and 2 and 3. So that is 16 bytes, bits, and this is 32. So you can read them as bits, read them as bytes, you can read them as words and doubles. It just depends how you want to handle it, but every bit is addressable as an input and output in the same manner. It's very important when you get to when you design your own thing, you need to know where the byte starts. And if you just remember, I'm just going to go back up one. The input starts at input 0.0 to 255. See, it's always starting at an even number. 0 is even. So just as a matter of principle, just remember to always reference your words from the even number. Just keeps life simple. Okay, analog inputs and outputs. In the good old S5 PLC, I don't know where my mouse went. Oh, there it is. The analog inputs would only give you 0 to 4095 as a raw value for whatever the actual analog signal was. So whether it was a 0 to 20 milliamps or a 4 to 20, 0 to 10 volts, etc., it would only give you 0 to 4095. So if you were reading a range of 0 to 100%, it technically gives you 1 divided by 4095 resolution, which is not bad, 0.02%. That's not bad for a level. I mean, a level in a tank, you're not really looking for 0.02%. You're looking for 1 or 2 or 3. So that's more than adequate. It was more than adequate then for a percentage. Here's an example. If it was an RPM reading coming in as an analog, say 0 to 4000, it would typically be a resolution of 1 RPM. So you didn't get very good resolutions of the analogs. Nowadays in the S7 PLCs, it goes to from 0 to 27648, and I could calculate, I think that's 12 bits. So you're getting now 0.0036 resolution on your levels. That's why you'll see it jumps around a lot, because it won't be 0, 1, 2, 3, 4. It's going to go 0, 50, 22, 61. So it'll jump around, and you can't really work with that. And again, if you look at the 4000 RPM, you got 0.14 RPM. Probably also not really relevant. Temperatures, you might have specific things, but it depends on the speed of the loop and something like that. All right, so that's analog inputs and outputs. Any questions so far?
Not from my side. I'm still good.
Okay, good. All right. Now here comes a very important area in the PLC. They're called markers. In the old PLCs, they were called flags, and they called them Fs. So you see, we haven't got M, MB, whatever, M. They were the F registers in the old PLCs. But again, it works exactly the same as the inputs and output bytes. There's marker 0.0, 0.1, etc., marker byte 0, 1, 2, and I've made the same mistake. You can address it as bytes, you can address it as words, you can address it as doubles. This is a very bad area to use in a Siemens PLC. Actually, back in the old days in the S5, all those inbuilt function blocks used to just assume and used to just take away your flag bytes 200s and use them and abuse them and switch them on and off, and you would come back from the call of the block and you didn't know what the hell that happened to your markers or your flags in that area. So I have as a rule, I don't use markers in anywhere in my programs. If you ever see it there, it's probably a very quick temporary check or test, but it's never, I never use markers. Avoid them. I use DBs. So everything that I want to control, I want to have control of. I put in data blocks, DBs, data blocks. And data blocks work exactly the same. They've got bits and bytes and words and doubles, but your program controls what goes on. There's no erroneous flags or function blocks which are going to use them. You control it. All right, memory is, again, as I say, data blocks, same bits and bytes and words. A reel is a 4-byte, so it's actually a double. So you'll see wherever you see a reel register in a PLC, it will always be a say DB100 DBD, data word double 0. And again, like I say, you control what happens in that program. So you control what happens to that DB. All right, what I'm going to do quickly is I'm just going to go and just demonstrate how we configure a PLC, either in step 7 or TIA, and I'll also show you the clock bytes. What I'm going to do is I'm literally just going to show you FML quickly, and then I'm going to go out and I'm going to do a live configure. All right, so here's FML. It has, now on the left hand side is the Explorer bar. You go to hardware, and there is the hardware on FML. Can I make this bigger? Used to be able to. All right. Anyway, here is the PLC. I can move it over here quickly. You can see it's configured as a CPU, as a 315 2PN DPN, but you can see here's the inputs. So if I literally now go and I scroll up here, you can see, I hope you can see, there is the first input card. It's a 32 channel input card, 24 volts DC, and you see it's assigned, well, it's been assigned address 0, input byte 0 to input byte 3. The next one is address 4 to 7. See, it's now 32 bits, and 8, you see now goes up in 4s. And literally what happens is when you start with a blank PLC and you put your first input card in, it will assume you want it to be at 0, but you can change it. Then you start making errors and issues, but that can happen. So you can see this rack, this is the main PLC rack, has got one output card at the end. You can see it's in a different column here, and it's also address 0. But this is Q0 to Q0.0 to 3.7. That's I, or input I 0.0 to 3.7. If I go to the other rack, there it is there. There's another output card. It's 4 to 7. This plant has only got 2 digital output cards. And there is an analog input card. There it is, starting at 256. Now you can see that it actually takes up, I'm going to quickly guess, 8 words. 256 to 271 is 8 numbers, so it's 8 bytes. And that's peripheral input word 256. The next analog is at peripheral word 258. So it's actually 16, I got it wrong. And you can then, on this S7, you can assign per 4 channels what input it is, whether it's a 4 to 20 or a or a 0 to 10, etc. You can change it on the config here. You see this little number down here, the C. There's a block on the back of the analog input card that it can go in a direction A, B, C, or D. So it's got a little arrow on it, and you have to turn it to point the arrow at C, and then the analog wiring inside the block will then work as a 4 to 20. If I change that to a 0 to 20, it's still the same. Okay, 0 to 20 milliamps. Oh, that's not helping me. Okay, let's go here. Resistor. See, it says A. So it's telling you you have to put that block on the A position. And if you don't do that, it doesn't work very nicely. So this is quite a trick with with the old S7 300s, the S7 400s, and the old S5s. They had the same blocks, whereas the new TIA, the 1500s, 1200s, you configure it in the PLC. So let me just go to TIA quickly. If I just open up, okay, open up Silo. Silo. So if I go to the I/O, the configuration, let me go topology. It's not helping. So there, oh, come on. There is the PLC. It's a 319, S7 319. It's actually a very nice PLC. But if I just double click it, it will actually show me the rack and slot. Now this has got nothing in it. It's got a CP card. It's not helping me. Let me go back to this. I'm going to go to the first input rack. You can see here is now the rack. It's got a power supply. It's got the outputs and input cards. And here on the right is the addresses. And you can see we're still stuck to the same numbering convention, 256. It's the first analog input card. There must be another rack with 0 and 4 there. But we always try and start at the same address every time. I go back. That's interesting. Yeah, see this one now is at 76. So you can assign them as this is now a plant which has been upgraded, but this plant has got a couple of racks, as you can see. It's got a couple of scales, but it's got. I'm trying to find the IRX. There's 1, 2. There's actually 6 IRX here. There's another one, another 2. Okay, so that's what you see. Let me go back out here. Let me go back to this, close the project. Let me go back to step 7. I'm just going to close this project. I'm going to make a new project, and I'm going to call it test 01. There it is. When you start a blank project, it has nothing. So you have to now insert a new PLC. So you insert a S7300 and it renames it. You can change the name. But the key is when you get to this, the first thing you have to do is go to hardware. And now you have nothing. You have no I/O. So on the step 7, you have to go to the Siemens 300 level in this Explorer. And you have to put a rack, a rail down. So you put a rack, a rail. And now you actually have a 12 slot rack. It actually is 12 slots. Okay, 11 slots. So then we're going to put a CPU in there. So let's choose, it doesn't matter, 315 2PNDP. What is important about 2PNDP is it's got 2 network, 2 Ethernet ports and 1 Profibus port. So if I go and put that in, it asks me for an IP address. I can just say new Ethernet, leave it as, now there is the first mistake everybody does, 192.168.0.1. Do not ever let me see that in a PLC. You must always, don't use 192.168.0. Choose another one. 192.168.216.100. Do not use that address because every Tom, Dick, and Harry has got his PC and his phone and everything on that IP address. All right. So there we have it. So you can see now it's really prompting me down here to put in IO cards. So I'm just to zoom this up a bit. So in the bottom here, so let me now go and put some IO in there. Now where's my IO? IO, digital input. So let me put in a 16 channel 24 volts. I'll drag it in here. You see automatically it's assigned 0 and 1. So it always assumes it's at 0, but I can change it. See, it's got system default. You can override it, but just try and keep your project. So that's 16 channels. Let's put another one in. Now you see, now what has happened? Okay, that is a 16 channel has gone 4 to 5. So that's now a mistake. So I'm going to go and change that, and I'm going to make that 2. So now it follows. And you can assign any address you want, but try and keep it in order. Just easier to fault find. And this one's now gone and mess it up. Murphy's Law, don't demonstrate. Okay, so I've got some input cards. I'm going to make some output cards. Let's put a 32 channel AC card in there, and it's gone and started at 12. That's not very nice of it. I'm going to make that 0. And then I'm going to put an analog input card in here, analog input. Let's put in an 8 channel 12 bit. Remember, 12 bit is 0.2727648. I've got to remember. Now it's gone and put it at 320. I've got no idea why I tried that. So let's go and make that 256. Now if I double click it, see, now it's telling me to put that thing on E. Now I don't even know what E is. That's very interesting. Oh, sorry, there's the block B. E is iron voltage, I think. So if I click on there, I can make it. That's not going to help me. So let's go there. E. Oh, four wire transmitter. Don't like 4 wires. 2 wire transmitter. 4020. Okay, 4 wire. You can change it 0 to 20. See the block there? C, D, and C and B. That is where you have to put that little block at the back of the card. So now let's just find out what that block of the card is. I'm just going to quickly go back to my desktop. I'm going to go over here. I'm going to try and find an analog input block here for you. I hope I've got the right manual. Anyway, this is what I downloaded quickly from the Siemens website. Just to show you, this is a S7 300. It's a 315 2PN. There you can see it's the latest one. But look very quickly, everything is limited. Number of blocks, 1024. Number of dBs, 1024. You can only have, you can call it dB 16,000, but then you can't have a dB 1023, and vice versa. And they can only be a maximum size. Function blocks, same thing. I just wanted to go where the inputs we've done. There are the input range. See, 2048 bytes. So this is a big beast. It can do double the size of the old 315s, and so on and so on. So again, I couldn't find. Sorry, I was trying to find the analog input card for you. That's not helping me. That's probably the wrong manual. Anyway, I'm going to get you guys to check that, but if we have a question, we can do that in the next session. Let me go back to my program. So let's leave it like that. You've got to do a save and compile. It seems to be happy. You go there and hardware is configured. Now it's automatically created a program for you. And there is our friend, OB1. It has a blank OB1 in there. And if I go in there, absolutely nothing's happening. So now I can do whatever I want in the program. Anyway, let's go to TIA and let's go and make a new one. Where do we go? Start. Create a new project. So let's go and do Tim 02 here. Create. Everybody happy so far? You see how to configure? Cool.
Yeah.
Okay, no problem.
Yes.
Okay, so here we have a blank program. Oh, this is interesting. I may have messed it up. Okay, let's go to first steps. Configure a device. Yeah, I'll do it here much easier. Show all device, add new device. Here we can go and put in a PLC we want. So let's go and put in this little one, 153. Come on. It tells us what it is. We go add. Chug, chug, chug. Takes a while. TIA. Okay, so there is our rack. Let me just move along a bit. So again, I can go into the hardware catalog. It's always, the look and feel is the same. If I now go and put a digital input card into this rack, it's going to put a 32 channel and you put it in, should be able to go in there. Oh no, hold on. Take that block, can put it in there. And you see, oh, there's, are you back? See there, it's assigned 0 to 3. I can literally copy that. If I go Control C, I can go Control V, and it automatically numbers it. I can go and put a digital output. See, it's put it in 0. This one works fine. See, quite simple. And the analogs let's go to analog input. Let's go, oh, I lost my rack. Where's my rack on? Oh, went over there. Okay, so I'm going to go here, put an analog input here. So it's going to put it at 12. I'm going to change that. I'm going to make that 256. And it does exactly the same as we had on step 7. So there it is. So that's the standard rack designed. See, it automatically creates an OB1 Kenobi. And there is your program. Now you can go and do everything in OB1, or you can go and structure it as you want. Okay, so let's go back to my PowerPoint. Wrong place. All right, so I was going to mention the clock byte. Okay, let's go back to our friend over here. Step 7. Let's go back to hardware. Okay, remember what I said to you about marker bytes. Marker bytes are dangerous, don't use them. But unfortunately, in our PLC here, if I double click on it, you get a thing here under cycle clock memory, and it's automatically here. If you click on this, it will assign a marker byte to you. I will, in my opinion, I'd never use marker byte 0, because every Tom, Dick, and Harry, they'll go and put 0, but I'm hurting myself when I say that, but I always make that a 1. So what happens with that, and I'll show you in the clock, is literally what happens. The PLC automatically has a inbuilt signal that will put the bits on in that byte every 0.1 seconds or 0.2 seconds or 0.5 seconds, 0.6. So you don't have to use a timer to create a 1 second timer, which you use for everything like we do on our programs. We just use bit 5. So we use bit 5. Everywhere we want to know when 1 second has gone by, we use bit 5. And that makes it very easy to program your PLC. You don't have to have any other bits. And you'll see what happens now that it's created that marker bit 1, marker byte 1. we can save it again. And if I go to sources here, yeah, sorry, I must go here. I have nothing. Okay, what I'm just going to do quickly, well, let's just do this. Let's close that. Let's go back to the PLC. I'm going to even try and download this to the simulator. Simulation. All right, so I'm going to download my program to the PLC. When all else fails. PLC sim, that is where it's supposed to be. Why? Murphy's Law, don't demonstrate. I'm just going to check something. It doesn't like me. Okay, I'll have to demonstrate another time, but let me just show you in my simulator what should happen if I could demonstrate. You see, I've already got in the simulator marker byte 1. It will actually show you these bits going on and off as the PLC scans. And that's exactly how it works in the PLC. If I go to TIA, they have a similar feature. I'm going to go into the CPU. Now this is what makes TIA different. It's got all these window panes that you've got to open up and close. And there's the system clock again. And you enable the byte there and you choose the byte. Just, you can see, look there, it actually shows you. They've actually assigned marker byte 0 as their default. I don't use that, so I'm going to take that off. And I'm going to enable the clock byte and I'm going to make that 1. And you can see now it's going to change them all. And those are the bits that we use for the clock byte. So that works exactly the same in TIA and in step 7. And it's a very important little thing that we use, because if I go into, okay, I'm going to close this one. I can close this program, open up FML again. If I go into OB1, I'll just go straight to global set global timers. What we do in this program, just quickly, is every second that you can see, if I go take it off, it's marker byte 1.5. Remember, 1.5 was every second. Every second, it's going to put this marker on automatically, and it's going to one-shot marker 2.5, and then this part here will make sure it's only one shot every second. So what really happens is we, in our program, we count with that 1 sec pulse. So literally every 1 second, it goes on for 1 scan, and we can then count how long it took. So we use, again, which I didn't cover, which I can cover again in the next time. Let me go quickly to my manual. Let's go back to some of the limitations of Siemens PLCs. I'm looking. Number of timers. There we go. This is now typical. You only had 256 counters, 256 timers. So if you wanted a timer for every input, a timer to go on, a timer to go off, that's 2 of your 256 timers. The bigger your plant, you're going to run out of timers. So when you start now sharing timers and doing all sorts of fancy things, it becomes a mission. I just avoid timers. We use our data blocks to have the preset for the timer and the actual, and we count in the actual using that 1 sec flag. we use that to count how long the timer is on. Let me just quickly digress. Let me go to a digital block, digital input block. Where is my digital 90? Yeah, this one is now a tricky one, but let's just go. Oh, this is a horrible one. Cancel that. FMO's horrible. Let's go to CMOL. CMOL were better. CMOL again, you'll see it's got the same timers. There's the same pulse count, 1 sec there. If I now go to my digital input block, see there's the 1 sec. It's used everywhere in the program as 1 sec. So if the input is on, every second it will count in this timer, in this block. And when it reaches the end, when it reaches the preset, it'll put the PV on. That is how we do timers in our programs, but I'll explain that more in the next time or the following one. Okay, so that is what's important about the clock bar. It's a very useful feature in Siemens PLC. Now, if I just digress, in Mitsubishi and Omron and some of the other Mickey Mouse PLCs, they have a lot of internal system bits and bytes which do the same thing, but you cannot read them via the COM. So you cannot see what's happening in the PLC via a remote SCADA or an HMI because they are system bits. So we just avoid them. We make our own clocks, we make our own timers, and we keep it simple. So let me go back to my, right, so just some useful tips. Don't use markers. I use marker bit 0 for special bits. Let me go back to just explain. Well, I've actually got them there on the screen. All right, so two things happen, well, a couple of things happen in the programs. We automatically assign marker bit 0 as a 0. It's always off. Global 1 is always on. So if you ever want to have an input in a block that's default to off, you can use global 0 rather than just put a 0 there and global 1 as an input. This global bridge is a very important feature which I've always used. You know what happens? Let me go to our PLC program. Let's go. Let me say some clever guy comes into my PLC program here and he says, this is not working. So I'm going to bridge it. So I'm going to do a bridge here. Oh, my bridge is not working. And I'm going to connect it to there. No, this one doesn't work. See, fortunately, but I can put something else there and I can bridge it. So if I use, in fact, I use a normally close there of the same thing. Now that circuit, if he saves it and runs it, it will never work because this program, this will always be either on and off. It will always be true. So now you actually don't know what he's done. You don't know where he's gone and buggered the program. But if for some reason you wanted to do that, you would then put in our M1.2 here. As I was, let me go back to my PowerPoint. M0.2, see, I even got it wrong myself. M0.2. And you can see now, I've actually done exactly the same thing. But now, in my program, if I save it, I can search everywhere where we bridged it. So we can go and see anywhere in the program where somebody at night maybe had a problem and they had to bridge something. And we can see now what's happened here. Somebody's gone and done a bridge here, look here. So what is going on here? Somebody's gone and made a, maybe this is me originally, there was supposed to be an extra bit there, but at least we know there's something missing there. Whereas if you've just got a link or something, you don't know where to find it, and you have some issues when you're trying to debug software. Then we have a simulate bit. I think at Food Corp, you know, simulate is very useful. This is the global simulate. So inbuilt into the software, if we put the global simulate on, we can literally, through that simulator, we can simulate the whole plant offline. The SCADA works, the blocks work, everything. We can, from the SCADA as well, click on an input and make it go on, and it will simulate that it's on like it was live. We use that a lot. And don't care is another bit we use just for, sometimes you have a function block that has an output, a Boolean output, and you don't want to use it. You just put the don't care on there, because if you don't assign something, you can't load it. There's our clock pulses again, as I showed you. So I use marker byte 0 for those special flags. I still call them flags, they're markers.
Sorry, Mr. Tim, if I may ask.
Yes.
Usually I see they use global 1.
Yes.
On the
okay.
program.
Yeah, I know. Yeah, that was a funny thing. Global 1 is actually in DB1. It is the same thing. There is 0 and 1. You can see it's set to true. You can use both. Those are default there. See, I've got all this, global.1. So in your program, it'll show global.1. So if I just go out of there and I do a cross-reference, and I change this to db1. What was it now? Sorry, let's go back. db1. 0.1. Okay, you're right. Oh, sorry. Murphy's Law don't demonstrate. Okay, so we go db1 .dbx 0.1, and there is where it's used in the program. And yes, you're right, there it is there. So that both of them work. And yes, it is a problem that there's no standard here, but both of them work equally. They have the same function. There are a lot of times sometimes
I can use,
yeah.
Sorry, Mr. Tim. I can use global 0 or global 1, it's still the same.
Now global 0 will be always off. Global 1 is always on. So let me go back to the DB. You see global 0 there is false, and global 1 is always true.
Okay.
So you can see now in this routing function block, there is I think this brand has only got 1 bin, so it cannot have a no bins signal. It cannot say to the routing that there's no bin available, because there is only 1 bin. So that bin has a high level, it will fault, but it never has a problem that it is, because it can't choose more than 1 bin. So that is bridged out. There's no pause either there. Well, the pause there is forced because further down in this logic, the pause is worked further down. So anyway, this is statementless. This is quite difficult to understand, and to my own defense, this was the easiest way to get it to work. But as you've seen in some of the new TIA projects, we've converted this all to structured text, and to me, it's much more readable than this horrible statement list. Okay, so you're quite right, Fani. There's global 1 and there is the GLB1. I was going to discuss DB1, 2, and 3 next time, but because the way I've done it, the way we've done it here, it creates a standard across all the plants. Okay, so you're quite right. DB1 is the same for those two. DB1, DB 0.0, and 0.1 are the same as those 2 bits. Okay, cool. Right, now I wanted to just, I don't know if you've ever done this before, but logic, everything in this PLC is a programmable logic controller. Everything works in Boolean. So whenever you say input A and input B must both be on, you're doing an AND function. And if you look here, this is what they call a truth table. So if you have 2 bits, A and B, there are 4 combinations in binary, 0 and 0, 0, 1, 1, 0, 1, 1. And if you understand a little bit binary, that's a 0, that's a 1, 2, and a 3. If you were to say that's the units and that's the 2s in binary. So an AND block the output of an AND block will only be true if both inputs are on. An OR block is either input A or input B. So here's the truth table for an OR. So it's the same 0, 1, 0, 0, 0, 1, but now the output can be on here because B is on. Here A is on. Both A or B is on, so it's also true. That's an OR. So I'll go get it now. Then there's what they call exclusive OR. This is a very interesting function. It means when either input A is on or input B is on, but not both, then the output is on. And you can see here, I'll put the truth table. So here, A is off, B is on, it's on. A is on, B is off, it's on. Both of them are on, the output is off. And that in Boolean, here is the Boolean expression. It's A dot B, so and. So if you had 16 inputs, it would be A dot B dot C dot C dot, etc. If you had 16 inputs and they were all together, it would be A plus B plus C plus D plus. And exclusive OR is A and the sort of circle around. Now, Boolean, I forgot to put your inverse logic. I meant to explain sometimes it is very, depending on your logic, it is sometimes easier to do the inverse of what you think. So if you're saying it's A and B and not C and not D, it's sometimes easier to do the inverse and then invert the results. So I'm just going to go quickly to a program here. I'm going to try and find something for you. Well, let's just take this rung here. I'm going to just zoom in again quickly. So here's a rung. This is step 7. So this is the ladder format. So if I go back to view here, I can put it into function block. You can see there's an and it's this and that, then that is true. You see that? And. So this, I don't know, this is the way they do it. And this is the reset. So let me go back to ladder again. So yes, so that's the branch to do that. If I put this into statement list, you can see now it's this and this and this, set that. You can see how the logic works. So there's and. And let me just see if I can find some ands and ors. Here's an and an or, If I change to function block, to ladder, you can see this is quite a complicated piece of logic. But in ladder, it's very easy to read. It looks like a wiring diagram. You can see that's a normally closed conflict. So if that is off, and that is on, and that is on, then the logic will pass. But this is now this and this and this, or this and not that and that. Now, if I just switch back to statement list, this is very difficult to debug when it's live, because you've got to understand what does this OR do. So this, the result of that logic now jumps over there. And it becomes very difficult to follow statement list. And I know the gurus in Siemens, they think they're wunderkinds in statement list. They can make it more compact and less instructions. That is true in the 80s and 90s. And these days we have so much RAM, we don't need it. And there's, just as an indication, FPD function block diagram. You can see the not, there's the not, little circle. So it's not that and that and that. There's the OR. That is the OR symbol in Siemens. German way. There's always another way to do it, the German way. And there's this input and not that one and this one. So it works exactly the same. So you need to get very comfortable with Boolean logic. I just wanted to see if I could show you in inverse logic. I can't remember offhand. Let me leave that for another day. So that's Boolean. You must know those tables off by heart. They will be your life. All right, so here's some homework for you. I want you to go to Google Siemens Industrial Mall or Siemens Mall, and I'm going to just give you a little tip here. If I go to my browser here quickly, where's my browser? I just Google Siemens Mall here, and the first one there is the Industrial Mall. So if I go open that link, it gives you a link into the industrial mall, and you can choose your country. So what I want you to do as homework, I want you all to register on the site. And if you go log in here, and it'll give you another screen. This is so your first time here, you go here and you register, and you choose your country, and you put in your email and all sorts of things. And Siemens doesn't answer back there very quickly, but in a day or so, you'll get a response, and you will be in. So if I go back here, and I log in, well, yeah, okay, let me log in. Hope I can remember the password. Probably wrong. Probably wrong. Oh, how's that? I'm in. Now, you can literally find here all the information you need about your PLC. So I'm just going to go quickly to automation. No, that's not what I want to go. Industrial controls and blah, blah, blah. Sorry, I was here. I thought I'd be so clever to show you. Oh, where is PLCs? Process control systems. There we go. Semantic PCS7. Okay, that's not helping. Sorry, guys. It's not so nice. Let's go there. Here we go. Controllers. This is not so nice. Semantic control systems. Anyway, in here you will find, you can even search for it, and you can find all sorts of nice information. Let me just show you. I downloaded this from Siemens, this data sheet on the S7300. I downloaded this whole document on the old S5155. It tells you everything about how this thing works, the beast works. You can download everything from the Siemens website. There's even an explanation on this document, all the different words and bytes and so on and so on. They get a bit complicated because they want to tell you everything, how clever they are. But go and download some things, go and search around. That's worthwhile. Go and download some stuff. The second thing I want you to do is go and Google what a Kano map is. This is now a very old name, but I even Googled that, and it just still does exist. It's got to do with Boolean, with Boolean logic. When you have more than 2 inputs, you now have to do what they call a Kano map, and it just helps you explain a little bit more about how Boolean logics work. And there'll be a test email to you on what I've shown you today. No, I'm joking. I'm joking. Anyway, that is it, guys.